Okay, thank you very much and good morning. As you know, the purpose is to present the Retrofitting project and some results that we achieved so far. The name of the project is Smart Retrofitting of Heating and Cooling System in buildings. The Retrofitting project brings together several small private companies, including engineering companies, manufacturing companies, and also academia and research institutions, and one industry association. As you can see, the project started in October 2016, and the duration is 48 months, so we are actually beginning the last year of the project. And what is the purpose of this project? Is to develop, integrate and demonstrate retrofit heating and cooling solutions that are easy to install and primarily energy efficient and cost effective. And we do this at two different scales, at building scale and at DC scale, using a combination of technologies, including PV, solar thermal, adsorption heat pump, vapor compression heat pump, and PCM storages on the building side. And concerning district, we developed a specific way of using waste heat, or to recover waste heat from wastewater, and use it for heating and cooling in district. And okay, these are the different phases of the project. And as I said before, we are at the final phase, at the beginning of the final phase, the evaluation. I cannot tell you anything about the evaluation, of course, but I can say a few words about the preliminary phases, namely design phase, development phase, and optimization phase, integration and optimization phase. And the idea is to develop 4 concepts and demonstrate 4 concepts, 3 at building scale and 1 at business scale. And now those 4 concepts, as I said before, are a combination or a configuration of different technologies working together. So we have one configuration that is bringing together solar thermal, vapor compression heat pump, and adsorption heat pump. Another configuration that is using photovoltaics, vapor compression heat pump, and PCM storage. And the third configuration, which is using a wastewater heat recovery system coupled to an electrical heat pump at district level for heating and cooling. Now, before getting into the design of each of those, we have to develop a design tool, a simulation tool, to optimally configure the different systems. And also we have to think about the control of the system. And for that we developed a self-correcting intelligent building energy management system, the so-called CRC2019. And I'm going to now show some of those results, namely the design planning tool, the adsorption heat pump that was developed for the project, the PCM storage developed for the project, and we developed the wastewater heat recovery system, and of course the CRC2019. Okay, concerning the design planner tool, the idea was to create a fast simulation platform. This is an online platform where you can, the user, or the planners, can enter some macro information about the building and the heating system and the cooling system, and quickly get an answer about the possibility to replace the existing heating and cooling plant with a new plant, which of course provide benefits in terms of energy savings and also economic savings. I will not go through the detail, of course, on the screen, but as you can see, the input layout is quite user-friendly. And Here is an example of a simulation result where actually you can compare the current situation with one of our configurations and discover, for example, that there are some benefits in terms of primary energy savings and benefits in terms of renewable energy contribution and also CO2 emissions. And also you have an indication of the payback period. There are also information regarding technical and regulatory information for the new system, because typically new systems bring in also new problems, let's say. And any information regarding the compliance according to the definition of NZEP according to the EU. Concerning the products, in our projects, we didn't focus too much on efficiency, trying to improve efficiency of the product. Actually, the purpose of the development was to improve the compactness, first of all, reduce the weight, and reduce the cost of such components. So that's why a company like Fahrenheit has developed a new absorption chiller with these exact purpose to decrease cost and decrease the volume and the weight of the system. And in a similar way, Sanamp is another partner of our consortium, has developed a new compact heat storage, PCM based, which compared to water can guarantee 56% reduction in volume, 40% reduction in heat losses, and most important is modular and scalable. So this really is the installation, especially in existing buildings where space for storages is normally not considered. And it's a dual ported heat exchanger, which means that you can simultaneously charge and discharge the storage, and this was a requirement of our design. And it was required by our, let's say, evaluation. Concerning the district solution, as I said, this is a wastewater heat recovery system, which is designed and operated by an Hungarian company, Thermowatt. And what they did specifically for this project was a new heat exchanger concept that is self-cleaning, because one of the major problems of this technology is the amount of time required for maintenance and the cost associated with the maintenance. So it was very critical to develop a solution that is self-cleaning and thus more cost effective. And last but not least, the SciBEMS is an architecture, as you know, the building energy management system that based on remote sensors and controls is able to keep under control what's going on in the building. And this is made through a gateway concentrator, which brings together the data, and an home agent through which the user can access locally or remotely the data and the controls of the apartment. And in our case, it was the radiator head, each radiators. At the same time, the gateway is a way in between the home and the cloud, with the cloud services like information management and comfort profiling and automation of control. Here is where we develop, let's say, new concepts that goes into the direction of modern predictive control and also automatic setting of the parameters that are needed to control the emission of the energy into the building in order to minimize the energy needs. Okay, so So having explained what we developed during the development phase, here I'm showing you some figures about the different demo sites and what we can see the different configurations that have been installed in a different demo, and also some figures about the size of the systems. And we cannot explain in detail how we came to those numbers for each of those these pilot sites, but I will anyway focus on one of those in order to give an idea of the work behind. So I chose Kosovo in Poland, which is I think an interesting case of a retrofitting system for heating. And the Kosovo pilot is in Poland, and as you know, the weather is quite cold in Poland. The building is an old building, is an historical building. It was partially refurbished recently. It's important to say that in each apartment, there are 12 apartments, gas boilers are used for heating and domestic hot water. And to a per-retrofit assessment, we evaluated the energy demand of the building for space heating and domestic hot water. And we designed a concept for retrofit, which I'm going to explain. So the idea is to add a centralized system that using renewables. You see here on the left, so we have PV and an electrical heat pump, which is mostly driven by PV, and a PCM storage that is used to preheat domestic hot water. At the same time, the electrical heat pump is able to contribute to space heating through a centralized heating loop. So there are 2 points of integration for our system in the apartments. One is the domestic hot water inlet of the gas boiler, and the other one is a heat exchanger in the heating loop of the space heating. And what is critical in this type of integration is to control very finely the operation of heat pump, because we want to deliver heat when it's needed, when the heat pump is able to provide heat, and provide heat to the space heating loop and not the opposite. And also, you would like to maximize the self-consumption of the production. So to do that, we did a simulation study in which we introduced the idea of the model predictive control. So we did the building model, the HVAC model, and also the controller model for this system. And we have used a transient simulation-based model of the building and the system as a way of comparison, and also a simplified model, a fast numerical model for the model predictive control. And based on the result of the model predictive control, we will be able to derive rules for the rule-based controller that will be implemented in the data set. So that was the idea of using model predictive control offline to have insights on the operation of the system and control strategies, optimized control strategies. So basically, the PCM is charged during central hours of the day, and the electrical heat pump is switched on based on outdoor temperature and information from the thermostats. We also did some analysis, sizing analysis, and because we have a degree of flexibility in our system, not only in the size of the components, but also in the type of material, for example, that we use in the PCM storage. Here you see comparison of 2 different organic salts with different melting temperatures and different sizes that goes together with temperature. There's a correlation, of course. and also different control strategies during the charging phase from the heat pump. Now, looking at the result, we can see that, of course, this option with the highest melting temperature is the one that can cover the largest share of domestic hot water from the heat pump. But of course, one can argue that having to charge the storage at a higher temperature, this solution could be less efficient in terms of energy, electricity consumption of the heat pump. And in fact, this is the case, as we can see in this other chart, where we calculated the seasonal performance factor and the COP of the heat pump. And what we see here is that, of course, there is a, let's say, higher COP for the solution with the lower melting temperature of the PCM. But anyway, it's also true that the first solution is good because it provides higher share of renewables. So the choice is always a compromise between these two factors. And what is important to stress also is the evaluation of the most important performance indicator, which is of course the seasonal performance factor, not the COP of heat pump. And here we see that there is a difference, a consistent difference between the two phases. Which brings me to the conclusion, so this brief overview of the project. We can say that the Retrofitting project proposes efficient and cost-effective renewable-based solution with a degree of flexibility. That's about 20%, 30% energy savings are achievable in these existing buildings through this retrofit solution, with a payback that is in the range of 10 years. This was based on simulations, of course, so we have to evaluate these in practice. For sure, modeling and simulation has been key in this process in identifying the best configuration and also the best control strategy in each pilot. And we believe that for the future, for applicability, we have to focus a lot on the simulation tools, because it's a lot of work to do this for designers, and also to work on the packaging, the pre-integration of the solutions, so that it will be easy to install, monitor, and then control in the future implementations. Okay.